program. This photo is of the first new Uranian satellite discovered by Voyager 2, called 1985 U1. It's a small, irregular sphere about 90 miles across. This is the NASA Science Report.
NASA's Science Report is a special summary of events leading to the Voyager 2 spacecraft's encounter with the planet Uranus. The programs originate live from the facilities of the Jet Propulsion Laboratory in Pasadena, California, and are authorized by the National Aeronautics and Space Administration. The NASA Science Report, Voyager 2 at Uranus, is one of a series of public information programs designed to keep the public informed of space exploration.
Hello, I'm Al Hibbs at the Jet Propulsion Laboratory. We're watching NASA's Voyager 2 as it continues its encounter with the planet Uranus. We're looking over the shoulders of Voyager scientists as they receive new information on Uranus and analyze it in its original form. We'll be discussing its significance, the mission's scientific goals, and what this encounter can teach us about our world and the universe. At 5 o'clock this evening, Pacific Standard Time, Voyager is 2,544,000 miles beyond Uranus, and it's traveling away from it at 33,172 miles an hour on its way to Neptune, the last planet it will visit, and it won't get to Neptune until 1989. Let's take a look at some of the more exciting photos that the scientists have been analyzing over the last 24 hours. This, for example, a backlighted picture of the dust in the ring plane. We've been taking many pictures of this, but it took a 90-second exposure to bring out this material. Tiny motes of dust with the sunlight shining through them from behind. These are the images of stars smeared across the picture because it was a 90-second exposure to bring out those. And then that amazing moon, Miranda, which has across its surface features that we've never seen on any other satellite or planet. Large geologic formations indicating something is happening beneath the surface, but not expected on anything quite so small. And this, another moon, Titania, which was filtered by a computer to bring out very sharp edges, emphasizing the sharp detail and sort of blurring out the gray in between. Notice how much detail there is on the surface and compare it then with this one. Umbriel, very bland, and yet they're both part of the same satellite system. And this Ariel, down near its lower, from this point of view, lower portion, canyons, where it appears that something is slumped down into crevices left perhaps by the surface pulling apart. And another view of Ariel, the complete one now, with similar canyons up at the top of the picture. All of these formations quite unexpected in bodies that were so small as this. With me now is Dr. Ed Stone, the Voyager project scientist. And Ed, let's talk about what's been happening today.
Well, as you've already pointed out, there have been some new images of the satellite surfaces, which again are quite interesting and are telling us something which we don't yet understand. In addition, this morning it was reported, we've managed to report the first measure of a planetary rotation period, or at least what we think may well be the planetary rotation period, a period of about 17 hours.
That was from the magnetic field data, or?
Actually, it was, we determined that by observing that the radio emissions coming from the planet had a certain periodicity to them, and that periodicity was about 17 hours.
And these radio messages are stimulated by the magnetic
That's
field.
right. Presumably they're tied to the magnetic field, which is then generated interior to the planet. Once we have a planetary rotation period, then one can determine how rapidly the winds are blowing, because we already knew that the clouds circulate the planet once every 16.25 hours or so. That tells us that the winds in that atmosphere are something like 100 to 200 miles per hour.
Compared to whatever it is responsible for the magnetic field.
Yes, compared to some deeper portion of the planet. That and the winds are blowing the same direction as the planet is rotating, which is somewhat of a surprise. We had really, I think, most had expected that because the poles were expected to be hotter than the equator, that the winds would be in fact blowing the other direction. Well, we also learned today that in fact the poles are not hotter than the equator, As far as we can tell, the planet to first order is the same temperature at all latitudes, although it is about 2 degrees colder at a small region at mid-latitudes. Again, quite a surprise.
But the cold spot then is neither the equator nor the pole, but sort of in between.
In between, that's right. Sort
temperate zones,
yes.
obviously.
And I think the best way to describe it is we just don't understand exactly how all of this is happening, but it's very clear that the atmosphere is not exactly what most of us expected it would be.
And we had, speaking of the magnetic field, this very odd offset of the axis of the magnetic field with the axis spin must mean some rather weird behavior of the magnetic tail of this planet as it blows back from the solar wind.
Yes, we would expect that if this is the sun, the magnetic field will wobble like this, that the whole magnetic tail will rotate like a sausage, if you like, with a 17-hour period, unlike anything we've seen before.
What about some of the, I've just been stepping through some of the pictures of the moon, but I didn't say too much about them. What about those?
Well, I think that the Umbriel is really an interesting moon in the sense that its surface seems to be the oldest surface in the system. It has very large impact craters, and it's a fairly soft-looking object. On the other hand, the other moons seem to have sharper and smaller impact craters, as though there has been the old craters have been erased, if you like, by a more recent bombardment. So we have, again, a variety of ages in the system.
We've been waiting for some time for the radio occultation data to come back. What does that show us?
Well, one interesting thing is it's shown us that, at least in the Epsilon ring, the particles there are likely to be larger than a meter across. This should be contrasted to Saturn, where most of the particles were a few centimeters. It is really a remarkably different kind of ring. These are particles which are this large rather than this large, dominating the rings.
Very surprising. Where are the little particles? I mean, these things must bump together occasionally, and there must be little particles knocked off.
Well, there are some small particles, and that's what the backlighted image of the rings that you just showed show us, that there are some, but there are relatively few of these small particles. Something is cleaning them out of the system as rapidly as they're produced.
And the ultraviolet, what are the early results from that one?
Well, on the dark side, we indeed found aurora. That is northern lights. There is a hot spot somewhat near what we believe is the magnetic pole. We're not sure exactly where it is yet because we have to map it out more carefully. But there's no question there is indeed a classical aurora on the night side.
Ed, thank you very much for that fast review, and we'll talk to you again later. The centerpiece of this encounter is, of course, the Voyager spacecraft. Let's go live now to Von Karman Auditorium to get a checkup on the health of Voyager 2.
And I'm Bill Griffith here in Von Karman with Project Manager Dick Laser. And Dick, you've started each of the press briefings each day with the statement that Voyager so far is working perfectly.
But I didn't say anything today, right? That's because it continues. I really didn't have anything to say. It's going great.
Do you do periodic physical examinations, if you will, electronically, periodically?
We're continuously monitoring the engineering data coming from the spacecraft, engineering data that describes the state of each of the subsystems and the instruments on the spacecraft. Then in addition, when we have time, and this will probably be after we get through the encounter time period, we do very specific tests to check out the memory of the computers and things like that.
During the Saturn encounter, you had that problem with the platform, jammed and so forth. We can go over to it now.
Why don't we do that? It's easiest.
How's it working now?
It's working perfectly. It did everything that we asked it to, and to the best of our knowledge, until we do the next one of the tests on this. As far as we know, it is in perfect health.
You corrected the problem.
That's right. Let me talk a little bit about how it works, and then we can talk about how we corrected it. This is what we call the scan platform, this whole device right here. And basically, it's sort of like an upside-down tripod, and all the instruments mounted on it can be swiveled around in azimuth or up and down in elevation. And basically what happened when we were just about at the time we were crossing the ring plane at Saturn was that the device that turns this in the azimuth direction, which is way up in that part of the spacecraft, it's sort of like a gear train. It got stuck. And we went several days without any pictures, any data at all from the science instruments on the scan platform until we kind of pushed it back to where it ought to be, and we got several nice parting shots of the planet.
This has been crucial, especially for Uranus, because you've had to take, and by the way, these are the two cameras here that have taken those fabulous photos, not only of the planet, but of Miranda and so forth.
The wide angle and the narrow angle, sort of like a telephoto and a super telephoto.
So if you hadn't had the platform okay for this encounter, you couldn't have gotten those high-resolution photos.
We would have been hurting. We had an alternate technique which involved rolling the whole spacecraft, more or less taking this whole spacecraft and spinning it around on the floor here. But that would not have yielded as good a mission as the one we just had.
Quickly, if you can, explain to us, I mean, the spacecraft was going 45,000 miles an hour when it passed by Miranda, for example.
Right.
And you had to correct the movement of the camera to get those high-resolution photos. How'd you do it?
Well, basically, I think you're talking about the target motion compensation, and what we did was pointed a target. I'll kind of point out toward the audience there. And then, if that target was moving, what we did was literally move the whole spacecraft. If we move the platform, it's kind of jerky, but we can move the whole spacecraft just at the right rate, very gradually, very slowly, and in fact, track that target so that it isn't moving in the field of view, just the background.
And I think it was you that said it in a press briefing that it's like shooting a race car that goes by
Exactly,
in
same
moonlight
principle,
at 45,000.
same principle.
Yeah. Thank you, Dick.
Sure.
Dick Laser, the project manager for Voyager. I'm Bill Griffith in Von Karman Auditorium.
We've talked a lot about pictures from Voyager, and we've shown you many of them, but Voyager can also see in the invisible regions of the spectrum, and one of Voyager's instruments measures infrared radiation from the planet and its satellites. And here now to talk about that experiment is Dr. Rudy Honnell from NASA's Goddard Space Flight Center. Rudy, what does the iris measure, and what have you learned from it? I believe it can do something about actually determining what the chemical nature of the atmosphere is, yeah?
That is correct. This picture here shows, so to speak, our raw material we work with. It shows the spectrum, which is the infrared color, if you wish. As a function, we call it wave number, but those are just different colors.
Mm-hmm. And this is the spectrum of the light that's being given off just because the gas sort of glows in the infrared.
Well, it's not so much a glow, it's a thermal emission. Every body emits a certain amount of heat, and we analyze the heat radiation. You see here two curves. One is a black one, which is a measured one, and this is our raw material we work from. Incidentally superimposed, you have here a red curve, which is a theoretical fit for 10% helium in the atmosphere.
So that particular concept, just that 10% fraction is the best fit to what you've seen in the study.
Well, it seems to be the best fit. Of course, there's some uncertainty. To include an uncertainty, we quote really 15% as an upper limit of the helium concentration.
Since you're measuring the thermal emission of the gases, you can also make a temperature map.
That's quite correct. And may I show the next slide here? What we have plotted here is the temperature in degrees Kelvin on the lower part versus atmospheric pressure. 1 atmosphere, that is the pressure of our own atmosphere on Earth. Of course, the atmosphere of Uranus is much, much deeper.
This is really only the top layer of Uranus.
This is only the top layer we can measure. And you see that it's not too different from our own atmosphere. It has temperature minimum. And then above that, the temperatures rise again into the stratosphere.
So our temperature does the same thing. A tropopause between the troposphere and the stratosphere.
That's correct.
This is coldest spot.
Except our atmosphere is much, much warmer than that one here.
That's about 350 below 0 Fahrenheit.
Right. What we have shown here are two temperature profiles. One for the dark pole, which is appropriately the dark curve. And the other one is for the light pole, which is the dashed red curve. Mm-hmm. What is so surprising to us is that those temperatures are almost identical. Also, the one pole has been exposed now for many years to the sun, the other one not.
About 20 years. It's been absorbing sunlight, the other's been radiating away heat.
But it shows that atmosphere is so massive that it has such a long thermal time constant that it hasn't cooled off. And a certain amount of dynamic forces may play a role in that, too.
You've also measured the temperature, I think, in more detail between the equator and pole.
That's right. Here's a temperature, the mean temperature at about 800 millibars, which is shown here versus latitude. 0 latitude corresponds to the equator, and 90 degrees latitude is the sunlit pole in this case. And here we show again temperatures, and it's only 1 degree Kelvin, which is about 1.8 degrees Fahrenheit, is from one tick mark to the next. So as a whole, the planet is extremely uniform, and
it's surprising that the coolest spot is sort of midway up.
That's right. The coolest spot is so between 20 and 30 or 35 degrees latitude. This is incidentally the latitude where the television people see those methane clouds.
That's fascinating, Rudy.
Everything seems...
Yeah. As more astounding results continue to pour earthward from Voyager 2, members of the news media from around the world hang on to nearly every word and event. We were there for this morning's news briefing.
Today's press briefing proved that the more Voyager scientists find out about Uranus, the less they actually know about it. For example, Uranus is a very cold planet with temperatures as low as minus 350 degrees Fahrenheit. But surprisingly, it turns out the pole on the dark side of the planet is warmer than the pole facing the sun. Dr. Andy Ingersoll said the temperature differences between the poles, therefore, are not caused by the sun, but by some unknown internal process. Some of the results of the radio occultation of Uranus are starting to come in. That's the process where Voyager took a silhouette of the planet by sending radio signals back to Earth around the planet and through the rings. The early data confirmed for investigator Len Tyler that the very dark rings are made of very large particles.
What we can say is that the particles are certainly larger than about 4 centimeters, which is about what this actually is, I think, if we were to measure it. And I suspect that they are much larger than the one over here on the right.
Larry Soderblom released this photograph of the rings with the sun as a backlight, and it showed very small particles between the rings.
But there's many, many other features in here. The estimated densities are such that it would be impossible. Well, it would be difficult to see these from the Earth. They're very, very diffuse, sparse material, perhaps only a few 10,000 individual particles, a micron in size per square centimeter. Very, very low density.
Soderblom also released a high-resolution photo of the mystery satellite, Umbriel, the darkest in the Uranian system, and as expected, it showed a distinctively featureless body.
If you look here, you'll notice that the surface of Umbriel is composed of overlapping mostly large craters in the neighborhood of 1 to 200 kilometers typical diameter. The crater-like form up here, this white donut, we suspect is in the floor of a crater about 150 kilometers in diameter. You also see a bright patch here that may be more of this bright material. Now, this bright material itself is only about 30% brighter than average Umbriel. So Umbriel is about a 15% albedo. This might be 25%, so still it's fairly dark material.
Project scientist Ed Stone said the latest data released only served to deepen the mystery of Uranus.
Each day it just gets better. We certainly didn't expect to find, I think most didn't expect to find winds which were prograde, that is, blowing the same direction as the planet rotates, yet that's exactly what we seem to have. I don't think many expected that there would be such a equilibration of the temperature between the equator and the pole, although that was always recognized as a possibility, but I don't think anyone really seriously considered that as what we would see. But now that we've seen it, we still don't understand it, and I think that also should have come through clearly this morning. We certainly didn't expect to find a dark polar stratosphere that was warmer than the sunlit side. And I don't know of anyone that suggested that we would find rings which were mainly meter-sized and larger particles, when at Saturn all the rings were mainly centimeter and smaller size. I mean, it's the difference between this. And again, it's just an indication that the Uranian system, as with the satellites, is just totally different than anything we've seen before.
With today's press briefing, I'm Bill Griffith.
One of the truly fascinating experiments aboard Voyager listens for waves that propagate through clouds of plasma, and those waves vibrate at audio frequencies. Don Gurnett of the University of Iowa is a member of the plasma wave team, and he's with me here to discuss it. How does it work, first of all?
Well, the plasma wave experiment is intended to measure waves and radio emissions in plasmas.
This instrument uses two long antennas, which are about 30 feet long. They're shown schematically over here in this diagram. These are the two antennas. Now, although the instrument was designed to study plasma waves, it turns out that it's also...
This is a wave like a pressure wave in air? Is a sound wave in air or something like that?
Sort of like a sound wave in air, only it's in this ionized gas that we call plasma. It turns out that this type of instrument is also very effective for detecting small dust particles that hit the spacecraft. The Voyager spacecraft, as it moves through the ring plane, is moving at a very high velocity. And when a dust particle hits the side of the spacecraft here, it essentially explodes. A small part, of course, if it were too big, it would go through and damage the spacecraft. So these have to be, we know they have to be very tiny particles. When the dust particle hits the spacecraft, it just explodes and instantly vaporizes and creates a very hot pulse of plasma, which expands and emits electrons, which are detected by the antenna.
So the particle doesn't have to hit the antenna directly. It hits the spacecraft, and then the plasma does it to the antenna.
We first detected this effect at Saturn, and our analysis is that we're detecting impacts on the spacecraft and not on the antenna. Well, we can detect these effects two ways. We have an intensity measurement in our instrument.
Well, why don't we hear what it sounds like? Okay. That's what I'm really interested in.
Well, let me describe how we detect the voltage difference between the antennas, and that voltage difference is amplified and transmitted back to the ground, and then we can convert it to an audio tape. And this is a recording of as we flew through the ring plane at Saturn, and what you should listen for is, it's like hail hitting a roof. Okay. A whole bunch of impacts, and I think when you listen to the tape, you can hear this effect. Hear all the static. The static consists of a whole series of impulses. Each impulse represents a small particle hitting the spacecraft, which we're detecting.
It wasn't designed for it.
It wasn't designed to do that, but it turns out the spacecraft has a very large area, and it's very effective at detecting such small particles.
Thank you, Don. I think you know we've been very busy here at JPL during Voyager's encounter with Uranus. We're not alone. For space scientists at many other facilities in the United States, around the world, busy on other missions planned for this year. Karen Long tells us what's involved.
Space exploration will never be the same after 1986. Major activities are planned every other month this year, prompting NASA to call this the Year of Space Science. We'll see new voyages to outer planets, international comet watching in space, never before seen views of the sun, space shuttle innovations, even a giant orbiting telescope to bring the universe home. This month's highlight, Voyager 2's encounter with Uranus. Now, scientists say they'll learn more in 10 hours than they've known in 200 years since the planet's discovery. In early March, an armada of spacecraft from Russia, Japan, and Western Europe will chase after Halley's comet. The European Space Agency's Giotto will dare to fly within 500 kilometers. That's just 300 miles from Halley's. It's risking total destruction from the comet's magnetic field and particles. NASA will also participate in the international Halley's effort by tracking the 5 foreign satellites from its deep space network, a series of antennas based at strategic locations around the world. We talked with JPL Chief Scientist Dr. Mustafa Shaheen about the joint project. Why is it the Russians, Japanese, and the Europeans not tracking their own Halley's missions? Why is JPL involved?
JPL is involved in it. From their point of view, we already have the best network of ground antennas to make observations of any point in space at any time we want. For the Russians to duplicate this at this time, it would probably be expensive. They have to go into treaties with many countries in order to have their antennas spread all over the globe. Likewise with the Europeans, I believe they feel that it is to their best interest, economically speaking, for the cost of their missions, to rely on us. We hope that this will be a precedent by which joint investigations, joint scientific investigations of planets will be done in the same manner.
NASA is planning some limited Halley's observations of its own, using existing spacecraft from other projects. According to Dr. Shaheen, NASA originally planned to conduct a major effort at Halley's, but budget restrictions prevailed.
The decision on selecting a mission at that time did not go in favor of a comet Halley, and we this year have missed the chance of having a dedicated mission to comet Halley.
What will we miss in the way of information?
We have expertise, longer term experience in observations from space. We have made some of the most impressive, most descriptive images of planets. We could have made images like this of a comet like Comet Halley. The Europeans, the Russians are going to have the capability to obtain images, but we believe that our ability, our experience would have played an important role in making our images by far more meaningful,
in other
more
words,
descriptive.
We could have put up a better craft, perhaps, and one that would take better pictures.
Yes, and also one that would have taken also different types of measurements that are not included on the European or the Russian spacecraft.
If all goes as planned in May, NASA will launch Galileo, one of the most sophisticated spacecraft ever constructed. Its mission? To fly to Jupiter and orbit the turbulent gas giant for nearly 2 years of close-range scientific study. When Galileo reaches Jupiter, it will drop this capsule-like probe down into the atmosphere. It'll pick up measurements on composition and temperatures and send them back to Galileo. And it may only be a matter of a few hours before the probe ceases to function. 5 days before Galileo's launch, the International Solar Polar Mission will get underway. Now known as Ulysses, the craft is designed to orbit the sun's poles, vast territory that has never been seen before. Just launching Ulysses and Galileo will be history-making events. It will be the first time any interplanetary craft is launched from space shuttles. During late summer, the long-awaited Hubble Space Telescope will be shuttled into orbit above the Earth. Scientists say it's a major turning point for space observation. They'll soon be able to look 7 times deeper into space, beyond restrictions of the Earth's atmosphere. Stars and galaxies some 12 billion light years away will soon be within our visual reach. Needless to say, 1986 will open a new era of space exploration. This year, as we celebrate the 10th anniversary of Viking's landing on Mars, we might also brace ourselves for discoveries promised in the coming decade. At Pasadena's Jet Propulsion Laboratory, I'm Karen Long.
I've been saying that Voyager can see in the invisible, and we've talked to Rudy Honnell, who studies infrared. Now I've been joined by Lyle Broadfoot, who studies Uranus in the ultraviolet, just the other end of the visible light from the infrared. Welcome, Lyle, and tell us what you found so far. One thing we announced today is quite exciting. The long-sought aurora has shown itself.
Yes, we had to move to the back of the planet before we were able to detect the aurora. It's we detected in a sequence that looks like this. That's the projection of our slit on the planet.
So that's a piece of the planet you actually sense with your ultraviolet sensor. Right?
And we scanned out this type of an array, and just as we moved up this far side, we found a very large signal in our instrument.
Is that where it's expected? Is that near one of the poles?
Yes, that's close to one of the poles.
Magnetic pole.
Magnetic pole, and we expect to be able to position the pole by using the ultraviolet.
How could you tell it was the aurora and not just? Well, you found so many different things in the ultraviolet, so many types of hydrogen glow, one sort or another. How did you know this was different?
Well, the spectrum is quite distinctive. On the dark side, we have this. We have the overlay here of the aurora. The auroral spectrum looks like this one, the green line, and on the day side, we have this other very large intensity from the Lyman alpha, and then again the overlay of the H2 emission. There's very characteristic differences in the spectrum.
I was going to say the aurora is caused, I guess, by charged particles coming down the magnetic field line.
That's right. The charged particles penetrate deep into the atmosphere and lose their energy by driving off electrons. Those electrons multiply and start to radiate. The energy then comes back out as radiation.
I see, and the other kinds of glows are stimulated by what? By sunlight, or?
Well, mostly by sunlight. On the day side, we usually see what we call day glow, which is a process by which the atmosphere absorbs the sunlight and then re-radiates it. In most cases, we know exactly what kind of process causes the radiation. Mm-hmm. This large signal in the center here that is saturated is actually an emission called Lyman alpha. It's the line of atomic hydrogen. It is backscattering the signal from the sun. It absorbs the photon from the sun and radiates it.
And you see this quite often in a big cloud around the planet.
That's right.
Hydrogen that's evaporating off, presumably from the planet now.
That's right. A corona. We call that the corona, and around the Earth we call it the geocorona.
So the Earth has the same thing around it?
Yes, Earth has. Hydrogen is the lightest of the materials. And therefore, if anything escapes from the planet, you can just be sure that it's going to be hydrogen
and that's
first.
what you found here.
That's what we found.
Well, thank you very much.
Thank you.
The distance from Earth to Uranus, 2 billion miles, is staggering. To travel an equal distance, you would have to cross the United States coast to coast 666,666 times. I don't know who figured out that number, but it's a beauty. Rich Terrell is a Voyager scientist who's good at putting that distance in perspective another way, and David Sparks talked with him.
Rich, everything that we hear about the Voyager 2 expedition and the planet Uranus is so filled with astronomical numbers, if you'll forgive the term. Would you regale us with some of your more down-to-earth analogies?
Let's try to put it into a perspective that at least we can visualize sitting here, and maybe everybody else can visualize as well. For instance, if the Earth, we can shrink the entire Earth down to the size of a head of a pin, okay? The Earth-Moon system turns out to be about 1 inch apart, and the speed of light at this scale turns out to be about 1 inch per second, okay? So we can imagine the Earth-Moon system. The sun would be about the size of a grapefruit, and it'd be about 45 feet away. And if you can imagine looking at a grapefruit from about 45 feet away, it's about the same size as the sun looks like to us in the sky. Now, Uranus turns out to be about 4 times larger than the head of a pin, so let's say it's a green pea, okay? And that pea is located now about 900 feet away, or 3 lengths of a football field away. So if you can imagine looking at a pea from 900 feet away, that's about what Uranus would look like from the ground, and that's what we have to contend with our ground-based telescopes. Okay, well, Voyager is going to fly past this pea at about 9 million miles away. It's about 4 feet away from the pea. It'll fly within a half an inch of this pea. So you can imagine the incredible view it's going to get of the Uranian system compared to the view we get from here. Another thing is that Voyager has to be flown at a very, very precise trajectory. It has to fly through a very, very small area of space and time at Uranus in order to bend its trajectory to fly onto Neptune. And Neptune is another pea. It's about twice as far away, about 6 football fields away. Now, the area that Voyager must fly through, 900 feet away from the head of a pin, is about the same area as that's swept out by about 1/10 the area of the eye of a needle.
Okay, thus far we have the Voyager going past Uranus and then on to Neptune, but once it leaves our solar system, can you give us more of your analogies about what we can expect it to meet?
Okay, well, actually, Voyager will be sort of on its own for the next 40 or so thousand years before it encounters anything else. And after about that time, it'll be encountering some of the nearby stars. Now, on the same kind of time scale, the nearest star to us is of course, the Alpha Centauri system. And that's another grapefruit, size of the sun. Only on this same length scale, it's about 2,000 miles away. So from here in Pasadena, the next star would be a grapefruit in Chicago. So that gives you the kind of scale of the vast emptiness of interstellar space.
The normal, usual way for a scientist to work is to gather his data, take it away, analyze it, think about it for what might be considered a long time, writes a paper on the results, the paper is published. It's thoughtful, considerate process. But these space missions drawing worldwide attention, we've become used to asking for what Voyager investigators call instant science. We found Brad Smith, the Voyager imaging team leader, and asked him about that.
It's called instant science.
Excuse me. Do you know exactly right now the diameter of the satellite? Could you confirm the diameters of the satellite? Because there was a kind of uncertainty whether they were... do you have the exact diameters of the satellites right now? I mean, precisely? Are they precisely known?
Could you explain a little bit about the apparent elongation of 1985 U1? Is that largely defect? Is that an artifact, rather, or is that something that likens it to some asteroid-type shape?
If you took the epsilon ring and rolled it up into one big gunky snowball, how would the size of that snowball compare to one of these new small satellites?
It is a phenomenon that seems to be unique to the American space program, and more specifically to planetary encounters. What happens is NASA scientists give their instant analysis of data just received from space after only a few hours, and in some cases only a few minutes analysis of that data. The leaders of the various Voyager teams have been in the scientific hot seat during the Uranus encounter, and no one has been in a hotter seat than imaging team leader Brad Smith. His team has had to make heads or tails of photographs of a very dark planet.
That's the problem. We are expected to do instant science. Tomorrow morning, we will have to stand up before 200 members of the press and tell what's in this image. And emotionally, we're sort of caught up between feeling absolutely elated that we have some remarkable science here to talk about, and feeling like complete idiots because we can't even identify the rings that we were talking about just a few days ago.
But Smith emphasizes that he is by no means complaining about having to perform instant science.
The American public pays for the space program. It's a very expensive program. They're putting out their dollars. They want to know what they're getting for their money, and that's reasonable, and we understand that. And the problems that we ourselves get into in trying to do this instant science is a result of the American public's interest in the space program, and that is gratifying. The fact that they really want to know is gratifying. But the hope is that somehow or other it will be communicated through the media that we are working under conditions that we don't normally work under. And if we make a mistake occasionally, that will be forgiven.
And while Uranus has produced some of the best science data of the Voyager mission, it has certainly been the toughest to analyze instantly because of its distance from Earth and the low light levels. This ring image is a good example. It arrived yesterday afternoon, showing the planet's ring system from the other side of the planet with the sun as a backlight. And by last night, Smith and his team still didn't know exactly what they were looking at. At today's press briefing, Smith had a bit more to say about that ring system.
The particles that are seen in the backlit image are small. We're talking about a micron or a few tens of microns.
Instant science. I'm Bill Griffith.
The magnetic field experiment aboard Voyager has been providing some of the most unusual and unexpected results we've received from Uranus. And here to talk with us about those results is Jack Connerny of NASA's Goddard Space Flight Center. Welcome, Jack, and tell us about these rather strange discoveries.
Well, I'd have to say that in terms of the space scientists that deal with magnetic fields and charged particles and all the exotic little creatures in the magnetosphere, the most disturbing or surprising result was the tilt of the magnetic field with respect to the rotation axis.
Certainly unexpected.
Well, if you look at the chart here, the direction to the sun is shown here. And of course, the spacecraft entered the magnetosphere basically along the planet sun line. We were all expecting a magnetic field, if any, to be aligned essentially with the rotation axis.
Like all the rest of the planets, more or less.
Like most of the, or all the planets that we've seen so far. And it's not just the planets we've seen and measured the field in. For instance, for the Earth, there's millions of years of records of the magnetic history of the Earth. And in all those millions of years, the magnetic pole has stayed close to the geographic pole, the spin axis.
It's reversed sometimes, but it's never gone
It
wandering
reverses,
around.
it flips one way, it flips the other, but it prefers that state where it's near the axis. And when we started studying the outer planets, we found Jupiter with a similar tilt, about 10 degrees, just like the Earth. And we expected Saturn to have the same sort of field, and we were all amazed at that time to find that Saturn's magnetic field was perfectly aligned with the rotation
No
axis.
tilt at all.
No tilt at all. And that runs contrary to expectations, of course, and it runs contrary to a lot of theoretical work that people have done for a number of years. So when we came to Uranus, we expected again to find a magnetic field close to the pole or even aligned with the pole. And the surprise was that it's almost an oblique rotator. It's almost, well, the pole is closer to the equator than it is to the pole. It's hard to accept, it really is. For instance, let me put it in real terms. If this magnetic field was what the Earth had, we'd have one pole, say, in Los Angeles, and the other pole would be in the Indian Ocean off Madagascar.
You used the word oblique rotator. It sounds like there is a name for such a phenomena. Are there other bodies in the world that have such behavior?
It is. In astrophysics, they have a lot of exotic phenomena that they deal with. Neutron stars, pulsars, and in their theoretical work to try to understand radio emissions and even light pulses from pulsars, they have as a part of their conceptual framework an oblique rotator, a construct, a gizmo.
So there is a theoretical notion that this does exist.
It's a notion.
But far away in stars, and certainly this isn't anything like a star. This hasn't gone through a stellar history. No. And yet that must supposedly has something to do with the motion of a conducting core somewhere in Uranus, which is moving around in a way that's totally separate from the rotation.
Yes, if you have a magnetic field, basically it means you need currents. And planets apparently like to generate such currents with motions of fluid in the deep interior. That's another problem for dynamo theories, this particular magnetic field, because it was thought by most people that you need convective, very heavy convective motion, like heating a pan of water, and you need to heat something in order to induce that convective motion. Now, apparently Uranus has a very, very low heat flux. They haven't measured it. It's so low to date. And so the question then arises, what provides the energy input to generate the magnetic field, and especially an
what provides this kind of motion?
Right.
Jack, thank you very much. It's one thing to send a spacecraft to a distant planet like Uranus. It's quite a different thing to get useful scientific information back. The key to that feat is the deep space network, the antenna complexes that girdle the globe and converse with the spacecraft. Karen Long is in the DSN's control center.
This is the control center for the worldwide deep space network, which tracks, commands, and gets data from spacecraft across the length and breadth of the solar system. One antenna complex is located at Goldstone, California, in the Mojave Desert northeast of Los Angeles. The antennas that track Voyager are 112 feet in diameter and 210 feet in diameter. A second complex is located at Tidbinbilla, near Canberra, Australia. Here, in addition to our own giant antennas, we're borrowing the great 210-foot Parkes radio telescope, 200 miles northwest of Tidbinbilla. Now, that's because Australia had the best view of Voyager and Uranus at the height of the encounter. The third antenna complex is at Robledo, Spain, about 40 miles west of Madrid. Two Spanish antennas are part of Voyager's network. So, while any part of the world is sleeping, somewhere a deep space network antenna is tracking Voyager 2 on its journey across the solar system. I'm Karen Long.
Now by Hal Mazursky of the U.S. Geological Survey, who's a member of Voyager's imaging team. And Hal, we've heard that Uranus may have been knocked on its side by some huge cosmic impact. Have you seen any evidence in any of the pictures, of the moons, or anything about the moons that might give a clue as to whether or not that happened?
Well, the moons have been very active in the past, and they're quite varied from inside to out of their distance from Uranus. But I don't think we see anything of that very early event. That probably happened in the very early history, and we think that the satellites are relatively young products. What we see now are stages in the evolution, the geological, evolution of the satellites.
Mm-hmm.
We think we're seeing much later stages, but those are exciting enough. And that brings up another thought, that is, now we've seen some spectacular pictures of Miranda.
Indeed so.
We've put them together in a mosaic, we've enhanced them, and we see some real differences from place to place. Now we get to the place where we have to synthesize some ideas, get some kind of consensus on what might explain these. And that brings us into an idea that was promulgated by one of the early geologists, and that is, don't seize on an idea and try to prove it no matter what. What you do is that's called a working prejudice. Instead, we try to devise various explanations and use multiple working hypotheses. You say, if this happened, then this is the geologic history. And you try to construct each of these, then match them with the evidence that we see in pictures and we'll get from the compositional measurements. Let's look at a couple of pictures of Miranda, for example.
This one is one that greatly intrigued me.
Well, I'd like to start with this.
Right?
Well, the reason for it is that there are these rounded off circles with bright and dark streaks. Now we have another kind of feature that looks like this. This is near the terminator, so you don't just see the bright and dark. As a matter of fact, it's very hard to see the bright and dark. What it looks like are ridges and valleys, again laid out in this squared off or circled off square pattern.
A little different, but both appearance and color are different here to here.
Yes, but now the question is the first one, bright and dark circles, and this one, the same kind of feature. We've had a considerable debate. Then it gets even more interesting because here's the end of that circle, and we have the chevron.
I mean, right down here, that's the end of that thing we're just looking at.
But the chevron has quite a different outline. It has quite rectilinear, angular, bright and dark things, and here we can see beautiful faults that bound those, and another fault that cuts across these. And then finally, tracing that fault off into the distance, here's the chevron again, and the small faults go off, and here we see an enormous fault scarp that we've measured.
That's a cliff.
That's a cliff that is probably at least 5 kilometers high. We don't have a very good number on it yet, but that has some striations on it. And that might mean the faulting has polished that and grooved that surface. So we know the sense of movement, and we see the topography offset. Now we have to put all of these ideas into something that fits together. And here's where our either working prejudice or multiple working hypotheses come in. And we've had a very interesting discussion this afternoon with, of course, universal agreement instantly on everyone's part.
I can imagine how much agreement there's been on everyone's part. Well, it's a baffling set of pictures.
Well, what really is interesting is you try to work on, say, an impact origin for all of them, and you fill stuff in. You have stacked layers. That was one of the early ideas coming in, that it's a volcanic thing with layers coming this way, that it's a great hunk that's been buried and is now re-exposed in the crust. But the fascinating thing is to say, take that idea and pursue it. Test it against the crater counts, the way the faults are, early, late, does it make sense? And that's where the real fun in our game comes in. The exciting part is planning it, carrying it out, getting the pictures down on the ground. Then the real battle starts of geologic ideas.
Wouldn't it be excellent if you could actually get out there and walk around on the surface, collect a few samples?
Yes.
That's right. This is the real challenge, to have to do it this way.
Yes, but you get very cold feet.
Thank you, Hal. As we've told you throughout this series of programs, Uranus is a fascinating planet. It's a discoverer, and the times in which he lived were fascinating, too.
Uranus was the first planet in our solar system to be discovered with a telescope. Because of its distance from Earth, it cannot be seen by the naked eye, so it was unknown to ancient astronomers. It was discovered by William Herschel back in 1781. He's a German musician who had settled in the English town of Bath, the cultural center of Great Britain at that time. Herschel was also an amateur astronomer, and with his brother Alex and sister Caroline, he built a 7-foot telescope he planned to use to catalog stars.
In the March of 1781, during this cataloguing of the sky, Herschel discovered one object which he saw on 3 consecutive nights. And on the 13th of March, he was convinced it was the same object. That object he thought was a comet. And he wrote up the paper which Watson delivered to the Royal Society later that year. And they became sure that it wasn't in fact a comet, but in fact a planet.
The planet was called Herschel as late as 1850. Then Britain's Astronomer Royal officially named it Uranus. In Greek mythology, Uranus was Saturn's father and Jupiter's grandfather. But Herschel's career took off as a result of his discovery. He was elected a fellow in the Royal Society and appointed King George's private astronomer. Dr. Gary Hunt is the Voyager team's unofficial historian on Uranus. He owns some of Caroline Herschel's private diaries. And according to him, Uranus's discoverer was a rather colorful man.
Herschel's life really was more than that pure discovery. He did a great deal more in astronomy, but had a very close relationship with the monarch, the king, and pretty through his connections with then Sir William Watson, as he later became. The king became a herd of Herschel. Remember, this is the period in the late 18th century. George III had been preoccupied by other things at that time, namely a little battle with the colonial states in America, and that had taken his mind away from astronomy. But George III was interested to learn about Herschel. He invited him to London, and Herschel came with his 7-foot telescope and star catalogues under his arm and presented them to the king. And the king said, well, if you're only an amateur, you will see how good you are. And the Astronomer Royal took the telescope and tested it at Greenwich and was convinced it was better than the professionals. So there we have, originally a musician who had developed telescope systems better than the professionals, who then had the royal patronage, and the king at that time gave him a salary of a civil pension of £200 a year, when the Astronomer Royal, the leading professional, was getting a mere £300 a year. Now, of course, salaries of that sort, when you get it from the monarch, they have little caveats, things you have to do for the king. And one thing he had to do was to entertain the king at court to show them the night sky when the need arose. Herschel, in fact, by now had moved from Bath to the small town of Datchet and ultimately settled in Slough, which is one of the places you fly over when you fly into Heathrow. And one particular night when Herschel had to go to the castle at Windsor to entertain the prince and princesses and the king and the queen himself, it was a typical evening in London, the London area, covered in cloud, therefore not a star in the sky. Herschel was worried. He had a salary of £200 a year to protect, so he rigged up a little model of Saturn, which in fact hid outside the windows, and therefore when the royalty looked through the telescope, they could see Saturn dangling there quite truly, and they were quite pleased, actually delighted, that they could see so much in the solar system. So his career was tremendous. He carried on his music throughout all of this, and I think he really has laid a tremendous foundation to not only the discovery of Uranus, but also in developing astronomy itself.
From the interactive room, I'm Bill Griffith.
Good story. Well, we're nearing the end of another day of tremendous excitement for the scientists and engineers of the Voyager project. And here again, to help us put all this into some sort of perspective, is Dr. Ed Stowe, the project scientist. Ed, we're still getting data down. Recorded data is still coming in now, so we haven't even got all the data, much less many of the answers. What's going to be coming up next?
Well, I think that we should be able to take the photopolarimeter stellar occultation of the rings and convert it into an image, very much like we did at Saturn. And some of those images, I think, will really show some quite amazing structure in the rings, some of which Lonnie Lane has already indicated with some of the early looks at it.
So with his graphs.
With his graphs. I think we can now make some images, and that I hope will be done by tomorrow. I think in the area of the atmosphere, the radio science occultation, the scientists there are working very hard to analyze the pressure versus temperature profile, and in turn interpret that in terms of how much helium there is in the atmosphere. This whole question of what is the helium abundance. And I think that is something which is now basically ready to be analyzed.
And is it likely also they'll be able to determine whether or not there are other things in the atmosphere that we can't quite see as clearly as we would like to?
With this particular investigation, they really only get what's called the mean molecular weight.
Right.
They can only tell what the average weight is, and so if there's something besides helium there, they won't be able to directly determine it.
But they'll notice that something is there that doesn't quite come out in the models.
That's exactly
Okay,
right.
Good.
Then I think we also will be able to say something more about the hazes in the atmosphere. There have been a number of reports from the imaging team about hazes, but I think with the photopolarimeter, which does very accurate measurements, we may be able to say something about the global distribution of the hazes in the atmosphere.
The photopolarimeter, we've been talking about working over just over the rings and getting all the structure there, but it's one big job is just the atmosphere
itself. And then in the magnetosphere, the data has finally come in, and today and tonight the scientists are working on it. I think we'll come up with a fairly comprehensive view of the distribution of plasma in the magnetic field. I think we'll have our first observations of what the plasma waves were like when the spacecraft was in the sun's shadow behind Uranus, and also what the high-energy particles are like that are trapped in that magnetosphere. So that's also something which is being worked on. And finally, in the case of the satellites, one missing piece of information has been what is their mass, so that we know what their density is, whether they're mainly water ice, half rock and ice, or mainly rock. I hope we'll have that answer by tomorrow as well.
How do we determine that?
Well, there are several ways to determine it. The way which I think may be the quickest is to take the optical navigation data where the orbits of the satellites were very carefully measured, and the satellites interact with each other and perturb the orbits, their orbits. And by measuring very accurately how they interact with each other, one can determine their masses.
It's a very tiny interaction.
A very tiny effect.
Accurate.
That's right.
The spacecraft has now gone out of the tail, of the magnetic tail of Uranus, is it not?
Yes, we have left the magnetosphere after having been in it for, I think it was, I've forgotten how many hours it was, but enough time so that I think we hope that we can have seen this tail rotate several times. And that should help us map out the structure, because from the standpoint of the magnetic field, you can think rather than the magnetic field is rotating as if the spacecraft is making a spiral through the magnetic field.
You draw from the magnetic field's point of view.
Yes, right. And so you get to map the magnetic field at an increasing radius and distance.
But we're still, even though we're outside of the magnetosphere, we're still getting signals that indicate what's happening inside of it.
We're still receiving radio signals, and those will be very important because the period which has been reported was reported from radio measurements before encounter. After encounter, we'll be able to monitor those same signals and add to the length of the database we have so that we can determine a much more accurate radio period for the planet.
And that radio period and magnetic period hopefully are the same period.
That's right.
The atmospheric features, has anything shown up when we flew by the planet and looked up close, the closest approach, looking down on the planet? Anything come up from that?
Just a few of the same clouds or plumes which were discovered earlier. It turns out the atmosphere, the clouds, the real clouds evidently are so deep in the atmosphere that they just normally aren't visible.
Well, now we're 3.5 days beyond Uranus and still receiving data, and we will tomorrow, Ed. Thank you very much for telling us about it. Tonight, all the scientists will be working hard, extra hard, to put together as cohesive a picture as possible of Uranus, its ring, satellites, entire environment out there, 2 billion miles from the sun. We'll be back tomorrow to bring you more of that picture. Until then, we'll stand down. I'm Al Hibbs.